This is the fourth part of learning and memory. Other areas of the brain that are involved with our learning and memory phenomena, again, I think it's really important to keep in mind mostly the hippocampus and the striatum and what their roles are. But we have also talked really pretty clearly about the amygdala in a different context because we talked about it in the emotion chapter, but its importance for classical conditioning is clear. People with parietal lobe damage, they don't appear to be able to elaborate on memory spontaneously. So usually when we're telling a story, what's happening is we are associating one piece of information with another, and we have this really elaborate kind of memory. And what's happening with people with parietal damage is they'll tell you something that happened, and in order to get those details, you would have to ask, well, where were you? Well, when was that? And they can answer those questions, but that kind of elaborating on memory is just not happening spontaneously. People with damage to their anterior and inferior areas of the temporal lobe have a semantic dementia. So this is really where it appears to be that our memory is for fruits, vegetables, animals, the things we've had experience with our lives that we know facts about, that information appears to be stored. People who have a semantic dementia might go into the grocery store and be very confused about where the vegetables are or what the word vegetables means. So their language, that has a lot to do with language. Your author talks quite a bit about not knowing which animals, like what are those stripes on the horse doing, when someone's looking at a zebra, as we just lose that semantic information rather than the episodic information. And we also see areas of the prefrontal cortex are involved with decision making, our working memory, our memory of rewards and punishments, and then how that influences our more conscious thinking about our decision making. That memory is involved there. So lessons from studying many different kinds of people with amnesia. Much of the brain contributes to memory. There can be deficiencies of very different aspects of memory with other aspects of memory relatively intact, where we see these double dissociations. Even though, of course, they communicate with each other and contribute to each other, one can behave independently. One area can behave independently of another area and vice versa. So there are these very independent kinds of memory, and various kinds of memory are going to depend on different areas of the brain. And that's my overall trying to say as much as I can and keep it as general as possible, even though, again, we've talked about some of the really important areas and their roles. Some of the basic questions that we want to ask ourselves when we're looking at learning and memory. And I alluded to these questions earlier, but they're really clearly questions we need to answer. One is, what are the changes that are occurring in a single cell during learning? And we can think of this as the changes in the pieces. And the second question is, how do those changed cells work together to produce adaptive behaviors? So what is changing between the cells really as we are learning? And this is a question of changes in the wiring between the cells. So we're going to start by looking at what's happening in a single cell. Okay, so the nervous system has to be adaptive. It needs to be able to change if we are to learn new information and if we are to be adaptive. And so when we look at the storing of information in the nervous system, it's often discussed as Hebbian learning. Donald Hebb in 1949 was quoted as saying, if axon of neuron A repeatedly or persistently excites neuron B, growth processes, metabolic changes, occur in one or both cells. And so a synapse that increases its effectiveness because the presynaptic neuron and the postsynaptic neuron are active simultaneously, that is going to be what allows us to be adaptive, and that's going to allow the nervous system to be adaptive. And so that kind of synapse, that when we have the neurons that fire together, wire together, so to speak, that's discussed as a Hebbian synapse because that is increasing the effectiveness of that connection that has been useful. This all makes sense as these kinds of synapses, as this kind of learning, as being involved in associative learning. So some of the early research conducted examining how we store information in the nervous system was conducted on the aplysia. This is a sea slug, and the sea slug has a very simple nervous system, very straightforward to examine. And we know that a nervous system is a nervous system is a nervous system, and once we know how a nervous system responds, we can extrapolate that to other animals and to other nervous systems. And I'm going to talk about habituation and sensitization as these kinds of non-associative learning. So in habituation, what happens is we decrease our response to a stimulus when it is repeatedly presented and accompanied by no change in other stimuli. We usually, in my classes, come up with some examples. And one example is the ding, ding, ding on your car that tells you to put your seatbelt on. And most of us just put our seatbelt on to stop it because it's a little bit annoying. But if you've ever just let it go, so I used to sometimes have my dog riding in the car and the ding would happen. And after a little while, you habituate. Okay, as we listen to something, we talk sometimes about the habituation of listening to the train whistle. If you live near a train, you eventually habituate and you don't notice as much that train going by as when you first move into a new apartment or whatever that's close to the train. So those are examples of habituation. What they did with the aplysia is they would have a small burst of air that went across that siphon. So this little area where they are sensing out there, and that little burst of air would at first cause this gill with the gill to withdraw, so this gill withdrawal reflex. And what they found is if nothing happened, so they would just keep puffing air past this siphon, that pretty soon that gill reflex would habituate and we would see it less and less. And basically, they also showed that this was not happening, that habituation was not happening at the level of the sensing or the feeling of that burst of air going by, and it wasn't happening because of fatigue of the motor neuron. What's happening is there is a change in the number of action potentials being sent down the axon of the sensory neuron, and a decrease in the neurotransmitter that is released at the synapse between the sensory neuron and the motor neuron, and that's causing a habituation. Another example of non-associative learning is sensitization, and it's always, so this is when we have an increase in response to a mild stimulus as a result to previous exposure to more intense stimuli. So my system, my autonomic nervous system is already aroused, and so a mild stimulus can then cause later for me to have a more intense response to that mild stimulus. And I'm using the word stimulus and stimuli, which is not always helpful for people, and so I usually have students come up with examples, and unfortunately they usually come up with examples that are more on the order of classical conditioning, where the mild stimulus is predicting something like a shock. That is an associative learning. If I see the light and then I get a shock, I'm learning that association, and that is not sensitization. Sensitization is I was in a state of arousal when I heard the mild stimulus. And so sometimes use the example of PTSD. So if I was in a traumatic situation and I heard some kind of boom, boom, pop, pop, pop later on, when I hear that boom, 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 pop, pop, pop sound, whether it is fireworks or popcorn or whatever, I might have a really intense response to that because of the autonomic nervous system arousal when I experienced similar stimuli before. We might notice that people with autism spectrum disorder sometimes sensitize to things that most of us habituate to, and that's because a lot of the times their autonomic nervous system is aroused when they are experiencing these really relatively mild stimuli. What's happening there is, so in this case, what they did to the marine mollusk, to the aplysia, is that they shocked the aplysia first, and then they gave that burst of air to the siphon. And so what they would learn to do then is that when the burst of air to the siphon came, they would do the even a more and an increased vigor of the gill withdrawal response. And what's happening there is now, if you remember, if we go back to that picture before, their sensory neurons are communicating directly to their motor neurons. Nice, simple nervous system, but there will be a facilitator neuron that can also be communicating there with the presynaptic terminals of the sensory neuron. And so that facilitator neuron is going to release serotonin to those sensory neurons. That's going to block potassium channels. And so what's going to happen is that neurotransmitter from the presynaptic neuron is going to be released for longer. So we're going to see continued release of neurotransmitter from the presynaptic neuron, and then sensory neurons will synthesize new proteins that produce long-term sensitization. So what we're talking about with Hebbian learning is really long-term potentiation. So these long-term changes that are occurring in the relationship between the presynaptic neuron and the postsynaptic neuron as one or more axons are bombarding a particular dendrite with stimulation. And so that postsynaptic neuron is going to fire. And I'm going to do this in this simple way, and then I'm going to keep adding pieces to it. So if we look at the presynaptic neuron, it is releasing neurotransmitter, and then if that's getting the postsynaptic neuron to fire, it's going to be firing rather slowly with the first presentation of the stimulus. So it's kind of fire, 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 fire. And as we get those neurons that fire together, wire together, as long as we are actually communicating directly, we see that there are changes. So in B, as continued presentation of the stimulus occurs, we're seeing changes in the presynaptic neuron. You can see that there is more area for neurotransmitter to be released. There's more neurotransmitter ready to go, basically, in that presynaptic neuron. And then also we see changes in the postsynaptic neuron, where we're starting to see some this is the building of receptors and the changing slightly of those dendrites. And we've looked at a picture before of showing dendritic spines that we can actually create spines in areas off this dendrite so that we have even more areas that receptors can go so that we can respond to in a strong synapse, so we can respond more efficiently. And so as we're seeing these structural changes later, that same stimulus is presented again, and what we see is much more neurotransmitter release from the presynaptic neuron, more places, more surface area, and more receptors for those neurotransmitters to affect the postsynaptic neuron. So now, as we're getting that same stimulus as we did in A, instead of this slow kind of fire, 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 that postsynaptic neuron is going to be going fire, 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 fire very quickly. So long-term potentiation shows three basic properties that make it an excellent candidate for how we do this kind of learning, how cellular change can help us to learn and remember. And the first of these is specificity. So it's going to be only the active synapses that are strengthened. And in fact, if we see those synapses that are not being used, we're going to see a long-term depression. Okay, as we're going to start to that synapse is going to be weakened, and we might even prune that altogether in our synaptic pruning to make this a more efficient system. We also see cooperativity, two or more axons simultaneously stimulating a postsynaptic neuron, and then that postsynaptic neuron firing. That causes stronger long-term potentiation than, say, a single axon in that kind of temporal summation, this kind of spatial summation with two or more axons. That's going to have stronger long-term potentiation. We also see associativity, which comes from these clearly. So pairing a weak stimulus with a stronger stimulus enhances later response to the weak input. Okay, and so I'm going to look at this picture with the neurons over there, and It's kind of hard to see for me on my screen. I know when I project it, it's large and it's easy to see. But if you look at the top axon, that's axon 1, and underneath that it says strong stimulation. And so we're just going to pretend, to make this easy, that the sensory neuron is axon 1, and the neuron that we're looking at, where all those neurons are communicating with its dendrites, that we're gonna call that the postsynaptic neuron. We'll pretend that's a motor neuron. And so what's going to happen, let's say with the strong stimulation, puff of air to my eye, that's going to cause me to blink. It's going to cause that motor response. And so that's going to be a very strong synapse. Let's just say I'm pairing a tone with the puff of air. So axon 2 underneath axon 1 there is axon 2, and underneath that it says weak stimulation. So let's just say there's a tone. Okay, let's just say before we pair our tone with a puff of air to the eye, we play a tone. The tone is going to not have a very strong synapse with a motor response to blink my eyes, right? Maybe I have a little startle response, but usually a tone plays boop, and I'm not going to do anything in response to that tone. But we are pairing these together, right? We're getting the boop and then the puff of air to the eye. And so now we're seeing two neurons, axon 1 and axon 2. Those two neurons are communicating to the postsynaptic neuron, and we're going to have a really strong response because I'm getting a puff of air to the eye and I'm going to blink my eyes. And so now that specificity, axon 1 and axon 2, are both synapses that are being used. They are active, and they are both strengthened. Because of the cooperativity, this is causing stronger long-term potentiation, and because of the associativity, we're going to see stronger responses to that weak input, to that tone, so that pretty soon that tone becomes a conditioned stimulus, and I am going to just blink my eyes to the boop because it's been paired with a puff of air enough times. And we can also talk here about long-term depression, because if we look over to your farther right there, axon 3 is showing there's no stimulation there. And so that is a synapse that is not active during this whole process of learning that the tone predicts the puff of air to my eye, and that synapse is going to be weakened and potentially eventually pruned so that we can make this a more efficient system. The other thing that Callet is showing in this figure, in this diagram here, is the figure at the bottom, which is showing time and how the baseline response of the postsynaptic neuron to the tone is very low. So this is to my axon 2, to my weak stimulation or my weak synapse there. And then as we are getting the two pieces of information together, so axon 1 and axon 2 are both stimulating the postsynaptic neuron. During that dark blue bar, we see this great raise in the amount of response that the postsynaptic neuron is now going to have to that to axon 2, which before had no response, and now my response is going to stay much higher. Okay, we're going to look at some of the biochemical mechanisms of long-term potentiation, because the question is, now we see how long-term potentiation could really help us to learn, but how does that actually occur? And I'm going to say mostly this is due to glutamate. We're going to be talking about glutamate here for a while. We're going to go back to some of the really early lectures on how neurons communicate and what's going on there. And so if you are not remembering that, you might want to go back and look at that before listening or after listening, and then listen again, because it is kind of complicated, where what's happening with the glutamate receptors, as we've talked about with several other different neurotransmitters, but relatively briefly, and really just alluded to how we have these different kinds of GABA, we have these different kinds of acetylcholine, different kinds of dopamine, and different kinds of serotonin, and they each get their different names, usually with either numbers or letters after the D1, D2 for dopamine. But for glutamate, they are named after the drugs that we discovered that influence these receptors. And so AMPA or AMPA, I usually call them AMPA receptors, are excited by glutamate and by a drug called alpha-amino 3-hydroxy 5-methyl 4-isoxazopropionic acid. I try not to say that one as much as I can possibly not say that one. But I usually say it once a semester, and that's it. From now on, AMPA. We also have NMDA receptors that are excited by glutamate and by a drug called N-methyl D-aspartate. So these people named their drug much more reasonably, in my opinion. But I'm going to call them NMDA receptors. And what's happening, so if we look at the picture that Callett gives us of the presynaptic neuron and the postsynaptic neuron, the axon of the presynaptic neuron is releasing glutamate, that widely distributed excitatory neurotransmitter. It is fitting into the AMPA receptors, okay, and that's allowing sodium to enter. So it is an excitatory neurotransmitter. If you remember, sodium is a positively charged ion, and so in that, that enters the cell through this ligand-gated channel that depolarizes the cell and raises its activation, its electrical potential. If we then look at what's happening with the NMDA receptor, the glutamate is, it would fit into the NMDA receptor, but there is a magnesium ion blocking that channel, and that's a positively charged magnesium ion, and it's going to be attracted to the negativity, right, the negative polarity within the cell. So it's going to be stuck in there, blocking the glutamate from getting into the NMDA receptor. So right now we're just allowing in sodium through the AMPA receptor. As we get enough activation, enough sodium and enough activation of the AMPA receptors so that the cell is depolarized, okay, that magnesium pops out of the NMDA receptor because it's no longer attracted to the negative polarity because it's no longer negative, and glutamate can activate the NMDA receptor, and the NMDA receptor also allows in sodium, but it also allows in calcium, which is also a positively charged ion. But calcium does a number of things. It has some it allows for metabolic changes within a cell, and so now we can activate a protein which sets a series of events into motion where we can, more AMPA receptors are built and dendritic branching is increased. And so as we just saw, well, earlier in about three or four slides ago, we just saw these changes can now increase the later responsiveness of the dendrite to incoming glutamate. Okay, so I've now strengthened that synapse by both adding AMPA receptors and more dendrites by allowing in the calcium through the NMDA receptor. And that is really, those are really the mechanisms of long-term potentiation.